Good morning to all. Today in this video, I am covering the topic current loop as a magnetic dipole, magnetic moment of a revolving electron. So let us start. The current loop as a magnetic dipole and its dipole moment. Now, as you have already studied that a current carrying coil, nearby a current carrying coil, the magnetic field is developed. We have also calculated the expression for the magnetic field along the axial line of a current carrying loop. Now, in a current carrying loop, if you look from this side, or when you look from one side of the loop carrying current, and if the current is anticlockwise, then the direction of the side of the loop behaves like magnetic north pole. Easy to remember that north. So in case of N, if you put the arrows at its end, then this will move like this. So it is the anti-clockwise direction. So in case of anti-clockwise direction, the side is north pole, and the other side where the current is clockwise. So from the S you can say that clockwise, so it will behave as magnetic south pole. The magnetic moment of this current carrying loop is given by I into A, n cap. N cap is a unit vector in the direction of the magnetic moment, and its unit is ampere meter. Now we will discuss how this magnetic dipole moment is IA. Now let us explain it in the following manner. Now Ampere found that distribution of the magnetic lines of force around a finite current carrying solenoid is similar to that produced by a bar magnet, which we have discussed in the previous lecture also, that the solenoid, current carrying solenoid, behaves as a bar magnet. Now this is the evidence that a compass needle when moved around these two bodies shows similar deflections. After noting the close resemblance between these two, Ampere demonstrated that a simple current loops behave like a bar magnet, and put forward that all the magnetic phenomena is due to the circulating electric current. So this is the Ampere's hypothesis. In the previous lecture we have explained that solenoid and a bar magnet, they are similar to each other. On the basis of that, the Ampere drew the concept that the current carrying loop or the circulating electric current behaves like a bar magnet. So now let us explain mathematically. The magnetic induction at a point along the axis of a current carrying coil. This we have discussed in the previous lecture. We have calculated the value of the magnetic field. B is equal to mu naught NIA square upon 2A square plus X square raised to power 3 by 2, where A is the radius of the coil and X is the point on the axis of the current carrying coil, and the direction of this magnetic field is along the axis and is given by the right hand thumb rule. Now for the points which are far away from the center of the coil, that is, if X is very larger than A or the radius of the coil, then A square is small and can be neglected, and for such point the magnetic field reduces to B is equal to mu naught NIA square upon 2x cube. And if we consider for n is equal to 1, means that is a single current loop whose area A is equal to pi A square, then this expression reduces to B is equal to mu naught IA upon 2 pi x square. So this expression reduces to this one. Now magnetic induction at a point along the axial line of a short bar magnet. Now this short bar magnet is similar to the electric dipole. So as we have studied in the first chapter, the electric field at a point along the axis of a short electric dipole, E is equal to 1 upon 4 pi epsilon naught 2q upon r cube. Similarly to that, the magnetic induction at a point along the axial line of a short bar magnet, the expression is mu naught upon 4 pi epsilon naught mu naught upon 4 pi 2m upon x cube, or mu naught upon 2 pi m upon x cube. So now equation 1 and equation 2. If we compare these two equations, then from here we will see that m is equal to IA. Hence, a current loop is equivalent to a magnetic dipole whose magnetic moment m is equal to IA. So, magnetic moment of a current loop is defined as the product of the current and the loop area. Its direction is perpendicular to the plane of the loop. So the current loop as magnetic dipole and its magnetic moment is given by IA. Now similarly, let us explain the magnetic dipole moment of a revolving electron. Now revolving electron. So according to Neil Bohr's atomic model, the negatively charged electron is revolving around a positively charged nucleus in a circular orbit of radius r. See in this figure, electron is revolving around a positively charged nucleus in a circular orbit of radius r. The revolving electron in a closed path constitute an electric current. The motion of the electron in anti-clockwise direction produces conventional current in clockwise direction, because conventional current, the direction of the conventional current is because of the positive particle. So electronic current, conventional current is always opposite to the electronic current. Now expression for the current, we know that current I is equal to Q upon T. So here Q is the charge of the electron, that is E, and time period is the period of the revolution of the electron. Now if V is the orbital velocity of the electron, then time period, that is circumference upon velocity. Velocity is equal to speed upon time. So from there we can, speed is equal to velocity is equal to distance upon time. So from here we can say time is equal to distance upon speed. So time period T is equal to 2 pi r upon V. Now using this expression in the above expression, we get I is equal to EV upon 2 pi r. Now due to the orbital motion of the electron, there will be a magnetic moment mu L. Now mu L magnetic moment abhi previous slide mein, that is IA, where A is the area of the orbit and I, the expression I from here, and area pi r square. So this expression for the magnetic moment mu L is equal to EV upon 2 pi r into pi r square, or mu L is equal to EV r upon 2. Now if m is the mass of the electron, then multiplying by m and dividing by m, the previous relation or expression reduces to mu L is equal to E upon 2m into mvr. Here mvr is the angular momentum L of the electron about the central nucleus. The expression for the angular momentum you have studied in class 11th. So angular momentum L is equal to mvr. So in place of mvr we can write L. So the expression reduces to mu L is equal to E upon 2m upon L, or mu L upon L is equal to E upon 2m, and this ratio is called the gyrometric ratio, and its value is constant because E is constant and m is constant. So ratio of the orbital moment to the angular momentum is a constant which is known as the gyromagnetic ratio. Now if we put the value of E and value of m, then the value of the gyrometric ratio comes to 8.8 into 10 raised to power 10 coulomb per kg. Now according to Bohr's hypothesis, the angular momentum has only discrete set of value given by the equation L is equal to nh upon 2 pi. This you have studied in chemistry also, that is angular momentum L is angular momentum has only the discrete set of values. L is equal to nh upon 2 pi, where n is a natural number and h is the Planck's constant, whose value is 6.626 into 10 raised to power minus 34 joule second. So if we substitute these values in equation number 1, so putting L in equation number 1, this will reduce to mu L is equal to E upon 2m into nh upon 2 pi and reduces to NEH upon 4 pi m. The minimum value of the magnetic moment, that is for n is equal to 1, this magnetic moment reduces to EH upon 4 pi m, and this X is known as the Bohr magnetron, or we can say that Bohr magnetron is the value of the magnetic moment for n is equal to 1. Now substituting the values of E, H and pi and m in this. So value of the Bohr magnetron found to be 9.27 into 10 raised to power minus 24 ampere meter square. In addition to the magnetic moment due to its orbital motion, the electron also possesses magnetic moment due to its spin, because electron is also spinning, and as well as it is revolving around the nucleus. So because of the revolution it has the magnetic moment, and because of the spinning it has a magnetic moment. So resultant magnetic moment of the electron is a vector sum of its orbital magnetic moment and the spin magnetic moment. So this is all about the magnetic moment of an electron revolving around the nucleus. Thank you.